I'm in trouble with this phone. Stupid YouTube. I don't know. Redundant transition. What the hell does that mean? Right. Anyway, um, I wanted to talk about some. I've been cleaning up actually. I've been cleaning my table. I moved a bunch of stuff out of the way because I couldn't see the wood for the trees. I was just getting really bad with cluster and everything, and I'm getting ready to wire my new coils. And I was going to talk about observations, conclusions over the last about 6 years or so. Right, just a minute. Right, so I got my new foam, this rubber stuff. It's self amalgamated rubber, which I put on these bobbins to keep the noise down on the solid state device. Now, so I'm going to be winding 4 new coils, specifically for the solid state device, which is over there right now. I had to move it out of the way because I couldn't move. I've just stuff everywhere. Right, so about the observations over the last few years, all the devices that I was working on that were rotary systems, you know, the disc system which used to be over there on the table, which I moved out of the way in the bedroom now because it was just collecting dust basically. It was just making it impossible to clean up because it was just so much clutter everywhere, and I've got rid of a bunch of plastic that was on the table as well. Just my tools on there right now. So one of the main things that have been the hindrance and the problem with the rotary systems is frequency, because as the system speeds up, some of the other things that I've noticed, and these are very important because it's in all rotary systems that I've been working on, including the drum system, which is this one here, the disc system. There's been situations when it's speeded up under a load. Now, not much, but a small amount. But then it starts to, as you increase the load factor, it would start to slow down. And once it got past that resonant tuned frequency, it would accelerate in its slowing down. It would slow down more rapidly. So, and then it would just basically lose all of its resonance and tuning. So it would basically end up drawing more current. So this is what I've observed in all the rotary systems that I've worked on. Now, okay, I could have used a speed governor. I could have used, but that's more circuitry. That's more power consumption when you're adding circuitry on and things like that. So when I originally built this H bridge, I'm just going to go over the H bridge. I'm going to move it over. It's not wired up right now. When I designed the H bridge, which is here, I designed it to to flip Alnico magnets, to change the polarity of Alnico magnets so that we could flip the pole, and it worked very well. But one of the issues with flipping, changing the poles of an Alnico magnet is saturation. You need to reach saturation point before you can actually change the pole of an Alnico magnet. I'm glad I built this. It's been really useful. Stick it over there out of the way a minute. So these are the, let me just grab these off here. So these are the small Alnico magnets that I've been using, which you can magnetize and demagnetize, and you can also flip pole on them. Now, it was an interesting experiment in previous builds where I had these in bobbins where there was a set of 4, and then I went down to a set of 3 in line, and I would consume quite a bit of power to flip the pole. But I want to explain about the reasons why those earlier solid state devices did not work. And the reason they did not work was because I think the best thing to do is for me to draw something out. Actually, it's a lot easier to explain it. I hope I'm live. Seems to be. Find a bit of something, a bit of paper to write on. Oh, this will do. Nothing much on there. Put these bobbins on here, cause... Right. Previous designs, I would have my coils. I'm just going to draw blocks actually. In the previous design, I had the actuator coil, AC for alternating coil, at one end. Then I would have my output coil, and then I would have another concentric, as in magnet array. So I would have early designs, I had a concentric, so I'm just going to put C. Then I had another output coil. Oh, this pen's coming apart on me. What's going on with it? Another output coil, and then I had another actuating coil on the end. This was the earlier versions where then I would, what the hell, I've lost my connection. I was pulse this side, then I would pulse that side, pulse this side, and it alternate. I had that system. And I used dual frequency resonance, where I was frequency resonating both sides. Yeah, YouTube is being a bit funny tonight. That was an earlier prototype system. What I'd got wrong was that the actuation coils were on the end and it was open-ended, so there was no feedback coupling to the other side. So basically everything was, it wasn't in balance. It wasn't a tuned circuit. So the actuating coil had concentrics here, you see. So the actuating coil actually had concentrics in there. They were actually yeah, anyway, so but the new system is completely different to that, because now we've got our actuating coil, which is sorry, I have a concentric here, sorry. Then we have our actuating coil, and then we have another actuating coil on the other side, and the concentrics in the middle. And because of that, it's balanced, so the magnetism doesn't care which way it goes. Either way, it's equal amount of balance. So it's I originally talked years ago, well, a few years back, I talked about the seesaw effect, where you have a seesaw. I don't know what you call it in America. I think you call it something else, where you put a weight on this end, and this end will lift up, and this end goes down, this end goes up, and it's in balance, so it doesn't require a lot of energy to move it, because both sides are equal weight, and you only apply a small amount of offset torque on this side to make it move. So this basically is what's going on with the concentric magnets in the middle. The flux, we have equal amounts of north, equal amounts of south, and south doesn't care if it's coming out this way or if it's coming out the other side that way, and vice versa with north. So when we flip the poles, we have a situation where we have a locked magnetic link between the two coils, so that the flux between these is flipped, but the extra energy that comes out this end is basically coming out untethered, or it's the lens effect is actually reversed, because we have a latching effect taking place in the middle here, and because of that latching effect, it's just think of it like when you bring two magnets together. Right, let's just get the two Alnicos. Right, so we have the two Alnicos. Right, one end is pushing away. Now these two want to come together, and we're just helping them. So we have our actuation coils here, and imagine the Alnicos with the actuating coils, and we're literally bringing them together, and they're locking. They want to stay together, and because of that, it's going to take a lot of energy to separate them, and that is why the lensing effect is not able to actually break that link, because it takes a lot of energy to actually break the link, and more so than the actual equal opposite reaction is actually able to do. So we end up with flux coming out the other ends quite freely. We have our circuit flowing through the core material, and without any worry about losing that linkage until the pole reverses, and then it basically throws them apart. The poles flip. Oops. The poles flip, and then it latches the other way. Yeah, that sort of thing. Anyway, I was trying to simplify it really to keep it very simple. But the thing about the solid state device as well is you can tune it, and it's fixed, the frequency's fixed. It doesn't drift around because there's no RPM change, there's no physical movement of anything, and there's no mass to move with magnetism, because magnetism isn't mass, it's instantaneous when it moves. When it flips around, it's well, not instantaneous, but it's very, very fast. Much faster than what we could do with a rotary system. This is why some people have had some success with rotary magnets that spin at very high speeds, but that's rather dangerous, and it's very noisy as well. So if you've got a small magnet that's tiny, that's spinning at like 10,000 or 50,000 RPM, you run the risk of that thing flying off and hitting you in the face, which is dangerous. I don't like going that fast. I wouldn't go there anyway. This is why people say speed is the key. But it is the key, but maintaining that speed is a problem, and it's difficult to maintain that speed in a rotary system because of external things like bearing, friction, air resistance. Because the faster you go, the more resistance, the more air resistance starts to play into it as you get faster and faster. That's when you have to get into aerodynamics and all that stuff. Yeah, but anyway, I just wanted to let you know, because from now on I think I'm just going to stick with the solid state designs. There's just a lot of advantages with that, and these new bobbins, when I get the coils wound on, they're going to be a lot quieter, because this rubber self-amalgamating rubber tape is what it's called, is brilliant, because I can even get it to creep up the side walls a little bit when I wrap it, which is what I wanted it. I ideally wanted it all the way to the edge of the bobbin drum, but nah, it'd be alright. So it should reduce the noise a lot. I don't know what the percentage is, because I'm not sure. I don't know. I haven't got any experience with it. Any experience with this tape. Ugh. But this is what it looks like on the. It's got backing tape on one side, and it's sticky, kind of sticky. It's weird sticky stuff though, because it doesn't feel that sticky, but when you keep your finger on it a while, it seems, when the heat seems to make it sticky more. It's weird stuff, but I was glad I got that. It's going to save me a lot of noise and irritation. Yeah. So anyway, that's it. Just wanted to talk about my thoughts, observations over the last 3 or 4 years, and why the rotary systems are just very problematic. And I'm really sad that I haven't been able to get this sorted out, this system. But yeah, there's still options open to me, like a speed governor on it, but as I say, yeah, it's physical, it's mechanical, it's subject to wear and tear, breakdowns and bearing problems and all sorts of things like that. So yeah, it's gonna end up, sadly, it's gonna end up in my well, I'm not gonna scrap it. I'm just gonna, it's a nice design. Yeah. I don't know if I'm going to end up nicking parts off it like the ferrite rings and stuff, but we'll have to see. I'm just going to keep it as a bit of a showpiece, I think, for now. But yeah, I'm probably going to need the bridge rectifier off it anyway. Um, but most of it is going to be left intact for now. I'll come back to it someday when I feel like I've got a new idea, a new method of yeah, keeping it in balance. If I do come up with an idea for keeping it in balance, but as I say, it's very, very hard to do that with a variable speed rotary system. It's very, very difficult, and I've found that out over the last 3, 4 years. Yeah, it's like beating your head against a brick wall. So anyway, thanks for watching.